In section 2, we're going to talk about vertical asymptotes and wholes of rational functions. And vertical asymptotes on wholes are something that occurs specifically when dealing with rational functions. So first let's talk about vertical asymptotes. So a vertical asymptote is a vertical line the function approaches as it heads towards infinity. So when we talk about these vertical lines, it's not something that you're going to be able to see on a graph, but it's something that you can kind of draw in yourself when you're looking at the graph of a rational function. So we're going to look at two graphs and identify the vertical asymptotes. So when you're looking for a vertical asymptote, you're kind of looking for a place that kind of breaks up the graph. So I look at this one on the left and I see if I draw a vertical line right here, it kind of breaks up the graph, and another one right here. So it's a place where my function doesn't actually have a graph. So if I'm looking at my vertical lines go through -2 and -1, so I have a vertical asymptote. I have x equals -2, and we have x equals -1 as the vertical asymptotes. And since vertical asymptotes are equations, you do need the x equals for them. My second graph here, there looks to be one place where my graph is kind of broken up, and it goes right, and it's going to be right here. So this graph only has one vertical asymptote, and it's through the x value of 2, so it'd be at x equals 2. So that's how you identify a vertical asymptote from its graph. But there is a way to algebraically find a vertical asymptote. So if you're looking at the equation of a rational function, the way you determine the vertical asymptote is you find the values of x that make the denominator 0 after the function is in lowest terms. So we're going to find the values of x that make our denominator 0, but we're going to first want to make sure a rational function is in lowest terms. So vertical asymptotes occur because the rational function is undefined for those values. So you can kind of think of vertical asymptotes as the values that make our denominator 0. So they go hand in hand with the domain of the rational function. So let's go ahead and find the vertical asymptotes of the following rational function. So we're going to start with r of x equals 4x over x squared minus 25. Because in order to find a vertical asymptote, our rational function has to be in lowest terms, we're going to want to factor our numerator and denominator. Well, 4x can't be simplified any further, so our numerator is already in its lowest terms. Denominator factor, x squared minus 25, is a difference of squares, so it factors as x minus 5, x plus 5. Now we look to see if any common factors cancel. And if I look, there's nothing that's going to cancel with our numerator. So this would be the lowest term for my rational function. So my vertical asymptotes, I'm going to abbreviate VA, occur at the x values that make our denominator 0. Well, x minus 5 equals 0 when x is 5. And x plus 5 equals 0 when x is -5. So we have two vertical asymptotes, and they are at x equals 5 and x equals -5, which are also the values that are excluded from our domain. Okay. Move on to our function q of x, which we have is x plus 6 over x squared minus 5. Well, the numerator x plus 6 can't factor anymore, so it's going to stay x plus 6. Our denominator, x squared minus 5, is still a difference of squares, but it's not going to look like a typical difference of squares. It's going to factor as x minus, and then the square root of 5 is going to stay the square root of 5, and then our second one is going to be x plus the square root of 5. And nothing is going to cancel. There's no common factor to cancel, so we're going to have two vertical asymptotes. And they are going to be at, and we have to figure out when x minus the square root of 5 equals 0, so x equals square root of 5. And our second one is going to be when x plus the square root of 5 equals 0, so x equals negative square root of 5. Okay. Third example is the rational function z of x equals 4x minus 8 over x squared minus 8x plus 12. So our numerator does factor. 4x minus 8 has, I can factor out a 4, and we get x minus 2 left inside parentheses. And our denominator, we want to find the numbers that multiply to 12 but add to negative 8, and that's negative 6 and negative 2. So it factors as x minus 2, x minus 6. So there is a common factor to cancel out in this one, and that would be the x minus 2 that appears in both. So our function z of x in lowest terms is 4 over x minus 6. So now there's only one vertical asymptote. And it's when x minus 6 equals 0, so it's going to be at x equals 6. So the last thing we have to talk about is something called a whole. So in that last example, we saw a common factor cancel out. So we have to talk about what that means, and that's where a whole comes into play. So a whole occurs when common factors cancel. In a rational function. So in that last example, we would have had a whole at the value of x that canceled in our common factor. So when things cancel, there's still a part of the function, but it's called a whole at this point. So when common factors cancel in a rational function. So we want to determine whether the domain restrictions are locations of vertical asymptotes or wholes. And it could be a mixture of the two. You can have both in a rational function. So our first example is f of x equals 3x squared plus 2x minus 1 over x squared minus 1. So we need to factor the numerator and the denominator. So in order to factor 3x squared plus 2x minus 1, I'm going to do that other method I showed you. So I'm going to do 3 times negative 1, get negative 3. I'm going to put 2 in this bottom. So I want to find the numbers that multiply to negative 3 but add to 2. And that's going to be 3 and negative 1. And then we want to divide both numbers by 3 and then simplify 3 over 3, which is 1. So my numerator is going to factor as x plus 1. And then negative 1 over 3 is written as 3x minus 1 as my second factor. Then the denominator, x squared minus 1, is a difference of squares, so it factors as x minus 1, x plus 1. So we have a common factor of x plus 1, so they cancel, and we end up with 3x minus 1 over x minus 1. So we had a common factor cancel, which means we have a whole. And our whole is going to be at that value that cancels. So x plus 1 would mean it'd be at x equals -1. And wholes are not vertical, they're not lines, they're just points at that x value. So at the x value of -1, if I were to graph it, there would be a little hole for that point. And then my vertical asymptote would be a line, and it would be the line that would make our denominator x minus 1 equals 0, so it would occur at x equals 1. Our second example is g of x equals 9x squared minus 4 all over 3x cubed minus x squared minus 2x. So if I look at the numerator, it's a difference of squares. It's going to factor as 3x minus 2, 3x plus 2. And before I start doing anything in my denominator, I recognize that every term has an x, so my first step is going to be to factor out that x. So we factor out the x, and we're left with 3x squared minus x minus 2. Again, I'm using the same method to factor the denominator, so 3 times -2, so I'm looking for the numbers that multiply to -6, that add to -1, and that is -3 and positive 2. Divide both values by 3. -3 over 3 is -1. So our numerator, 3x minus 2, 3x plus 2, and our denominator now becomes x times x minus 1, 3x plus 2. We have common factors of 3x plus 2, those cancel, and g of x in simplest terms is 3x minus 2 all over x times x minus 1. So there was a common factor, so we do have a whole, and it's at the x value that makes it 0. So 3x plus 2 equals 0 when x is -2/3. And then we actually have 2 vertical asymptotes left. So the x means we have a vertical asymptote at x equals 0. And then x minus 1 means we have a vertical asymptote at x equals 1.